Welcome, calculus students, to related rates, our last topic of the first semester. And these are all going to be word problems where you set up an equation and then relate some rates. So let's look at this first example where we've got a cone being drained of water. Now, don't worry so much about, do I have to memorize all my different formulas? You can jot them down, and I'll jot down the particular formula that applies in any given problem. It's a matter of you figuring out how to relate the rates, because this equation here just relates the three variables: volume, radius, and height. And all of these change as the water is drained out of the cone. The volume certainly changing, the height is dropping, the radius is getting smaller. But they change at different rates, and there's different units of change on each of these as well. So we start with the original equation, and you can differentiate implicitly with respect to t to obtain the related rate equation. That's almost going to be universal in these, is that we're taking the derivative with respect to t, or time, to get the idea of a rate. So here we go. The power of 3 is a constant multiplier, so it just comes out in front. And then you have to use the product rule on r squared times h. Leave r squared alone, take the derivative of h with respect to t. Leave h alone, take the derivative of r squared with respect to t, and that's 2r dr dt. So there you go. You've got an equation now that relates the rate of change of volume to the rate of change of both h and r. Now just a quick word about some convenient notation. I've found that over the years, this x dot is a lot easier to write and say than dx over dt. Same thing with y dot. So the problem I just did, we could actually state the final equation this way. dv dt is v dot equals pi over 3 times r squared h dot plus 2rh r dot. And now you can compare that to the original equation. This related the variables, volume, radius, and height, and this is relating the rates: rate of change of volume, rate of change of height, rate of change of the radius with respect to time. So, how is this different than our old notation of y prime? Y prime was generally reserved for derivative with respect to x. So, a few things. The dot is easier to say than dy dt. And the dot specifically for applications for taking the derivative with respect to time. And that's the main gist of related rates. And the prime notation often gets confused with the first power when doing complicated derivatives. I think if you use prime as an abbreviation, sometimes people might think it was y to the first. Here it's not that different, but when it's handwritten, it can be confusing. Okay, let's try some of these. Okay, y and x are related by this equation. Y equals x squared plus 3, and they're both differentiable functions of time. Find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. Well, let's first just start by taking the derivative of both sides with respect to time. The derivative with respect to time of y equals the derivative with respect to time of x squared plus 3. So we get here dy dt equals derivative with respect to time of x squared plus the derivative with respect to time of 3. So we said an easier notation to say y dot, and derivative with respect to time of x squared is 2x x dot plus the derivative with respect to time of 3 is 0. So here's our equation that relates the rates. Y dot equals 2x x dot. Now, we have to find dy dt when x equals 1, and given all these other things. So we have x equals 1, dx dt, which is x dot, that equals 2 when x equals 1. So we're all set. Y dot equals 2x x dot, so sub in, and you get 2 times 1 times 2 is 4. There you go. Y dot, which is equal to dy dt, is equal to 4. Now, that doesn't mean y dot is always 4. It's just 4 when x equals 1. It also said when x equals 1, dx dt was 2. So you have to look carefully at the given information. Okay? Now, here's a summary of what we just did in the last problem. There's an equation, and usually a given rate, and maybe some given specific values for the variables, and then you find dy dt when x equals 1. You have to be careful not to sub these variables in too early. Notice I didn't put x equals 1 in at the beginning of the problem. I took the derivative of both sides with respect to time with both y and x as variables because they do change. And that's what you have to be careful of in related rates problems. What is a variable and what is constant? So here's our next problem. The total area as the outer radius increases. So that'll change as the ripple spreads throughout the pond. Pebbles dropped in a calm pool, causing ripples in concentric circles. The radius of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet across, at what rate is the total area A of the disturbed water changing? So, the radius and the area are related by area equals pi r squared. The rate of change of the radius is dr dt equal to 1. That's what it says right here, when constant rate of 1 foot per second. So what's the equation? Well, it was just mentioned. That's area equals pi r squared. And the given rate is the dr dt, the rate of change of the radius. And what are we supposed to find? The rate of change of area when r equals 4. So, we can proceed as we did before. We take the derivative of both sides with respect to time, and then the chain rule gets applied in both these cases because you've got pi r squared, the derivative of r squared becomes 2r, but then you have to take the derivative of the inner function. And then you substitute in the values. We're given dr dt equals 1 when r equals 4, and so we get 8 pi. So when the radius is 4 feet, the area is changed at a rate of 8 pi square feet per second. Now here's some guidelines for solving related rate problems. Identify all the given quantities and quantities to be determined. Make a sketch and label the quantities. So these are variables. Write an equation involving the variables whose rates of change either are given or are to be determined. Use a chain rule, implicitly differentiate both sides with respect to time. And after you complete step 3, substitute in the resulting equation all known values for the variables and their rates of change. Then solve for the required rate of change. This is key. Notice step 4 here. This is subbing in of the specific values of the variables. It happens after you do the differentiation. Here's just a few examples of how you can identify rates in a problem. And a lot of times it comes from just looking at the units. The thing that has units per unit time, that's going to be your given rate, or the rate you're trying to find. So here's an example of blowing up a balloon. If you put in air at a constant rate, will the balloon's volume increase at a constant rate? Yes, but the radius won't. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So let's look through our given information here. Our given rate is this rate of change of volume, dV dt, 4.5 cubic feet per minute, or 9 halves. It's a constant rate. It's not like 9 halves at 2 seconds and 3 seconds. It's 9 halves all the time. And we're supposed to find what dr dt is when r equals 2. So we start with the equation. And, I'll have these equations right there on the test. It's a matter of you interpreting the equation correctly. Or there might be a choice of some equations just to jog your memory. Volume equals 4/3 pi r cubed. And so now we can take the derivative of both sides with respect to time. And there's that constant multiplier rule, the 4 pi stays there. And the derivative of r cubed is 3r squared. So you see how the 3 came down the front. Let's show the first step over here. Derivative with respect to time of volume equals the derivative with respect to time of 4/3 pi r cubed. So we get dV dt equals 4/3 times the derivative of pi r cubed, so the constant multiplier rule, both those were constants. And the derivative of r cubed is 3r squared dr dt. So the 3 and the third cancel out, and that's where we get to 4 pi r squared dr dt. Now solving for dr dt, isolate this dr dt, and you got 1 over 4 pi r squared times dv dt. So now you can put in r equals 2 for the radius, and put in 9 halves, and you get about 0.09 feet per minute. Now notice the volume was increasing at a constant rate, but the radius was increasing at a variable rate. Just because two rates are related does not mean they are proportional. In this particular case, the radius is growing more and more slowly as time increases. Do you see why? Go back to the original balloon problem. And I'm sure you've seen this effect when you're trying to blow up balloons. You keep on putting the same breath of air in with each time you're pumping into it, and after a while it seems to be slowing down because it's getting so big. It's increasing by the cube of the radius. Okay. Now, here's another problem. An airplane is flying at an altitude of 6 miles, s miles from the station. And we're tracking it. If s is decreasing at a rate of 400 miles per hour when s equals 10, what is the speed of the plane? So the plane's actually traveling in this path, but our radar stations give us information about this distance and how this distance is changing. So, let x equals the horizontal distance from the station as shown in the figure. Note that s equals 10 when x equals the square root of 10 squared minus 36, which equals 8. So what they've done here is, and this is where you have to be careful, you've got this s equals 10, and you can sit there and use Pythagorean theorem on this, 6, 10, to figure out this distance x. X squared plus 6 squared equals 10 squared. X squared plus 36 equals 100. X squared equals 64. X equals 8. Or maybe some of you saw that was a Pythagorean triple. It's the 3, 4, 5 doubled. That's not the whole problem. That's just figuring out how the distance this x is at this particular time. X and s both change. This 6 stays constant, but these two are changing as we start sneaking in here like this. And we're going to have a different triangle here, a different value of x and a different value of s. And we want to see how these two rates are related. Because the radar station has been able to give us the rate of change of s, 400 miles per hour. Does that mean this plane's going 400 miles per hour? I don't think so. Let's take a look now at the problem. You're given ds dt equals negative 400 when s equals 10. dx dt, find dx dt when s equals 10 and x equals 8. So x squared plus 6 squared equals s squared. That's Pythagorean theorem. Take the derivative of both sides with respect to t. Notice the derivative of the 6 squared is just a constant, so that's 0. That disappears. And you get 2x dx dt equals 2s ds dt. Divide both sides by 2 and by x. So you get dx dt equals s over x ds dt. Now we can substitute the values in. 10 in for s, 8 in for x, negative 400 in for ds dt. That was all given. And you have negative 500 miles per hour. Because the velocity is negative 500 miles per hour. The speed, which is the magnitude of velocity, you can just say the positive part, the 500 miles per hour. It says negative because it is getting smaller. X, if you look back at the original diagram, as the plane moves in here, this side of the triangle is getting smaller, as is s. And that's why ds dt was given as negative 400. Okay, here's an accelerating object now. In the last example, we had a plane that was flying at a constant speed overhead. Well, the radar tracking station was saying it was coming at constant speed. Actually, we saw by the relays that had changing speed. So, here we are. I think, hold it. Okay, find the rate of change in the distance between the camera shown down here and the base of the shuttle up here 10 seconds after liftoff. Assume that the camera and the base of the shuttle are level with each other at time equals 0. Okay? Now, the shuttle's rising with this position equation, s equals 50t squared. So that's handy that they gave it to us there, where s is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. So we've got another right triangle again. Let's see how that comes into play. So we're given some rates, ds dt, that is, it's 100t. Because we get that from s equals 50t squared, we actually have to do a little derivative equation. You have that s equals 50t squared. So the derivative of s with respect to time is changing. It ends up being 50 times t, 2t times the derivative of time with respect to time, which is just 1. So that's where you get 100t ds dt, or s dot equals 100t. We want to find dr dt when t equals 10. So we can relate the rates with the Pythagorean theorem, because this is a right triangle in here. So r squared equals 2,000 squared plus s squared. Take the derivative of both sides with respect to time. The 2,000 squared, that's a constant, so that just falls out. Derivative of r squared is 2r dr dt. Derivative of s squared is 2s ds dt. So dividing through by 2r, we get dr dt equals s over r ds dt, which equals s over t times 100t. Remember how we said ds dt was actually a variable equation. So now when t equals 10, you know that s equals 5,000. From this equation. And you obtain r equals 2,000 squared plus 5,000 squared is equal to 1,000 squared to 29. So we actually have to figure out what this initial, or what's capping at 10 seconds. So find the rate of change of the rock when t equals 10. So we've got s, which is 5,000, r, which is 1,000 times the square root of 29, ds dt, when t equals 10. Oh, there's the 100 from this equation. So taking this equation down to here, and there's the 100, and then the time is 10. And you get 928.48 feet per second. Okay, flange out.